Hello, my dear students. Welcome to my class Physics. Today's topic is collisions. It is a complete concept and complete class note of the collision. Let us proceed. What is a collision? A collision is an isolated event. The term isolated means there is no external force acting on the system. In this event, two or more colliding bodies exert relatively strong forces on each other for a relatively short time interval, due to which the direction and magnitude of the velocity of colliding bodies or particle change. The collision occurs when the bodies either physically touch or collide, or if the path of one is affected by the force exerted by the other. So, for collision to occur in actual physical contact is not necessary. That means, number one, what is collision? A collision, it is an isolated event. It is an event, isolated event. That means when there is no external force acting on the system. Only action interaction taken place between two or more objects. Another point is, it is not so necessary that two colliding objects, they will come in physical contact to each other. In our daily life, like for example, collision between or in any case of accident, we are observing that two colliding object they will come in contact with each other, but that is also collision. But in some cases, especially in cases of the atomic subatomic particles, there is an experiment given by the Rutherford Mason, and in that experiment, alpha ray scattering experiment, the alpha particles, that is nothing but the helium nucleus, when it is moved toward the gold nucleus, at that time there will be no physical contact but collision is taken place. That means in collision, a large amount of force acting very small interval of time, and even the force may exert by keeping some distance. It is not so necessary that two objects will come in contact, and at that time, at that interaction, there is a large change in the magnitude of the velocity of any one, or in direction also there is change in the momentum. When you study the collision, there are two key rules of the collision game. The two rules, key rules of the collision game are: number one, law of conservation of linear momentum, and number two, law of conservation of energy. And now we proceed about the different type of collision. And first of all, elastic collision. A collision is said to be elastic collision if both kinetic energy and momentum of a system remains conserved. Practically, linear momentum that is conserved for all types of collisions, but only kinetic energy is conserved in elastic collision. Therefore, alternatively, we can define the elastic collision, a collision in which there is absolutely no loss of kinetic energy. That means here the key point is the kinetic energy. For example, colliding between atomic and subatomic particles are elastic collisions. Practically, collision between two ivory balls. Ivory means it is the teeth of elephant. Ivory balls can also be taken as an elastic collision. Now, the basic characteristics of an elastic collisions. Number one, the linear momentum is conserved. Practically, it is conserved for all type of collisions. Total energy of system is conserved. That is also conserved for all types of collision, and that is the common features for all types of collision. But the special is the kinetic energy is conserved. That is, obviously, the kinetic energy in such collisions is not converted into any other form of energy, like heat energy, sound energy, etc. And it is taken place when the forces involved during elastic collisions are conservative forces. That means here the collisions forces involved during the elastic collisions must be conservative forces. Otherwise, if one or more than one non-conservative force involved in this collision process, in such a case, some amount of kinetic energy will be converted into heat energy, sound energy, or in other form of energy. In such a case, the total kinetic energy will not remain conserved. Here, the key point is that kinetic energy is conserved. All other, the linear momentum, total energy, these will be conserved in any type of collision. It is the common features. And another special point is in perfectly elastic collision. the all forces involved in the collision process are conservative in nature. And our next type of collision, that is the inelastic collision. The collision in which momentum of the system is conserved, but kinetic energy is not conserved. This type of collision is known as the inelastic collision. That means momentum always conserved, but kinetic energy is not conserved. Obviously, some amount of kinetic energy convert into other form of energy. Or therefore, we can alternately say the collision in which there is loss in kinetic energy during collisions. For example, collisions we come across daily life are generally inelastic collision. In our daily life, we are observing different type of collisions, and almost all these are non-elastic collision, inelastic collision, because always there are some amount of kinetic energy converted into heat energy, light energy, sound energy also. And here the basic characteristics of an elastic collision we stated above, that the linear momentum is conserved, total energy is conserved. It is the common feature for all the collisions. Number three, that is kinetic energy is not conserved. That is the main point, main difference between the elastic and inelastic collision. Obviously, a part of kinetic energy is converted into some other form of energy, as for example, heat energy, sound energy, etc. That means some amount of energy always convert into other form of energy, some amount of kinetic energy, obviously, and therefore the after the collision, the kinetic energy will be less than the collision before the collisions. And here, some or all the forces involved in an elastic collision may be non-conservative in nature. And due to this involvement of the non-conservative nature, we know when any work done by the non-conservative force, that energy dissipated, maximum time it dissipated into in the form of heat energy. Now another type of collision, it is also inelastic collision, but known as perfectly inelastic collision. The collision in which the two bodies after collision stick together and then move as one body with common velocity. That means after collision they stick together and they are moving with common velocity. This type of collision is known as the perfectly inelastic collision. In this collision, momentum is conserved, total energy also will be conserved, but the loss of kinetic energy will be taken place. And here, the loss of kinetic energy into other form of energy will be maximum. For example, when a moving bullet hits a stationary wooden block, then the bullet, let us suppose, gets embedded into the wooden block and then moves as one body having common velocity. This type of collision is known as, is an example of perfectly inelastic collision. And in all cases, we are in all the above three types of collision, we are observing that either kinetic energy remains same or that will be less after the collision. But somehow in some cases, the kinetic energy after the collision will be more. It is not such a collision, but it is also sometimes we are saying the super elastic collision or explosive collisions. It is the collision in which there is an increase in kinetic energy. That is the reverse effect. Generally, kinetic energy remain conserved or it will be less after the collision. But in some cases, when explosion taken place during the collision, some other form of energy convert into kinetic energy, and therefore, when the kinetic energy after the collision will be more, this type of collision is known as the super elastic collision or explosive collision. Practically, we are not considering this type of collision as a pure collisions, because some other external energy, source of energy are involving here. It occurs when there is a release of potential energy on an impact. For example, bursting of cracker when it hits the floor forcefully. At that time, after the striking the floor, the different fragments of the cracker will have possessed more amount of kinetic energy than before the collision. Now, one very important term related to the collision, and that is the coefficient of restitution or coefficient of resilience, and it is written or denoted by the small e. In actual practice, most of the collisions between real objects are neither perfectly elastic nor they are perfectly inelastic. These collisions are practically partially or semi-elastic collisions. In such collisions, the kinetic energy reduces, so the speed of separation is less than the speed of approach. The degree of elasticity of collisions is determined by a quality or a quantity that is known as the coefficient of restitution or coefficient of resilience. That means in our daily life, all the collisions somehow they are not perfectly elastic collisions, but there is some how one part of the collision, or it is nearer to the elastic collision or very less than the elastic collision, and that means how much percentage of collision elastic collision, 70% elastic collision or 80% elastic collision, etc., etc. The degree of the elastic collision that can be denoted by a quantity, and that quantity is known as the coefficient of restitution or resilience. And how can we define it? The coefficient of restitution or resilience of a collision is defined as a ratio of the relative velocity of separations after the collision. Obviously, the relative velocity of separation that will be after the collision to the relative velocity of approach before the collision, and it is dependent by the E. Mathematically, if we write the E equal to relative velocity of separation after the collision and relative velocity of approach before collisions. And now, what is the relative velocity of separation and what will be the relative velocity of approach? Obviously, before the collision, the collision will take place only when the two objects comes near to each other. That means they are approaching to each other. At that time, the velocity difference is known as the relative velocity of approach. And in normal cases, after the collision, the object they separated, and there will be some relative velocity of separations. And that is obviously after the collisions. And before the collision, approach is taken place. After the collision, generally separation is taken place if it is not a perfectly inelastic collision. So E equal to relative velocity of separation after the collision divided by relative velocity of approach before the collisions. Let us suppose E1, E2 are velocities of the two bodies before the collisions, and V1 and V2 are their respective velocities after the collisions. And then E equal to V2 minus V1 divided by E1 minus U2, and we can get better understand from this figure diagram. Let us suppose the two objects A and B, their masses M1, M2, they are moving along the same directions, along the same straight line, and U1 approaches toward the object B, that is before the collisions. Otherwise, the collision will not taken place. That means when U1 greater than U2, at that time only collision can be taken place. Both since they are moving along the same directions. At that time, U1 minus U2, it is known as the velocity of approach, relative velocity of approach. That means relative velocity of A with respect to B, that is U1 minus U2. And now collision, that is an event, isolated event taken place. And after the collision, generally they get separated. And let us suppose the V1 is the velocity of the first object, that is A object, after the collision. And V2, that is the velocity of the second object, B object, after the collisions. Now, generally V2 greater than V1, and therefore V2 minus V1, that is the relative velocity of separations. And the ratio of the relative velocity separation, that is V2 minus V1 divided by U1 minus U2. Here the relative velocity is U1 minus U2, and it is a relative velocity is the V2 minus V1, since V2 greater than or equal to V1. Therefore, we can write E is the V2 minus V1 divided by U1 minus U2. Obviously, it is a pure number because it is the ratio of the two relative velocities. There will be no unit, no dimensional formula, dimensionless quantity, but variables. For perfectly elastic collision, the value of the E will be 1. That is relative velocity of separation after collision equal to relative velocity of approach before collision. That means these two are equal. These two are equal for the elastic collisions, since there is no loss of kinetic energy. Perfectly inelastic collision, there is no velocity of separations, relative velocity of separation, because they are moving with the common velocity. Therefore, V2 minus V1 will be 0, and therefore E will be 0. Relative velocity of separation after collision will be 0 for perfectly inelastic collision, as two bodies after collision stick together. Now, for inelastic collision, the collision is not elastic collision or not perfectly inelastic collision. For intermediate collision, that is for inelastic collision, E lies between 0 and 1. That means here the relative velocity of separation is less than the relative velocity of approach. That relative velocity is not 0 or not equal to 1. That is between the 1 and 0. That means it is a fractional number. The smallest value, therefore, we can say now the smallest value of the E is 0 for the perfectly inelastic collision, and the maximum value of the E, that is the coefficient of restitution, is the 1 for a perfectly elastic collision. The value of E depends on the material of colliding bodies. As for example, for the two glass balls, E that is nearer to the one, that is 0.95, and for the two lead balls, E equal to 0.2 only. That means when two lead ball collide to each other, maximum amount of energy, kinetic energy loss into heat energy or other form of energy. The coefficient of restitution can be used to distinguish between the different type of collision as under. Now, from with the help of this quality or quantity, we can distinguish. Obviously, when E is equal to 1, E is equal to less than 1, E is equal to 0, we can this. Elastic collision or in one dimension now. Our topic is elastic collision in one dimensions. And what is the one dimension collision or what is the one dimensional motion? That means one dimensional means when the objects are moving along the same straight line, same line without any change the directions. That type of motion is a one dimensional motion. Similarly, one dimensional collision also similar to that fact. It is a collision in which the colliding bodies move along the same straight line path before and after the collisions. That means same straight line path, same line along the same line before collision and after collision, the colliding object will moving along the same line. Then this type of collision is known as a elastic collision in one dimension. These are also known as the head-on collision. One dimensional collision is also somehow known as the head-on collisions. Let us consider two bodies A and B of masses m1 and m2 moving along the same straight line with velocity u1 and u2 respectively. Let us see this example before the collision and after the collision. There will be along the same line, and therefore this type of collision is known as the one-dimensional collision, or it is also known as head-on collisions during collisions, after collisions. And we are considering the elastic one. Elastic one, that means here the kinetic energy also remain constant. When E1 greater than E2, then the two bodies after some time collide with each other. After collision, the two bodies move along the same directions with velocities V1 and V2. Let us suppose therefore total linear momentum of the system before collision, that is the m1 e1 plus m2 u2, and total linear momentum of system after collision, that is the m1 v1 plus m2 v2. That means v1 and v2, these are the velocities after collisions. In this event, the known quantities are m1 and m2, u1 and u2, and unknown quantities are v1 and v2. That means here, what is our target to study these topics? We have to find out the v1 and v2 in terms of m1, m2, e1, u2. Also here, we also prove that we have to find out the value of the E in this collision. And this collision is elastic collision and one-dimensional collisions. Now we can always get this equation. There is a law from the law of conservation of linear momentum. It is the total linear momentum before the collisions, and it is the total linear momentum after the collisions. And always we can apply the law of conservation of linear momentum in all type of cases, all type of collisions. So here we also can write that m1 e1 plus m2 u2, which is equal to m1 v1 plus m2 v2. Or from that we can just simplify it. f1 from right to left, that is the minus m1 v1, and m2 v2 minus m2 u2 by taking the common m1, that is the u1 minus v1, which is equal to m2 into v2 minus u2. Since the kinetic energy is also conserved in elastic collisions, because we are considering collision, it is elastic collision. Therefore, total kinetic energy before the collision and kinetic energy after the collisions, these two will be equal to each other. Half m1 e1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Half is common, therefore we can write this. And by taking the m1 in one side of the equation and m2 other side of the equation, and therefore m1 e1 square minus m1 v1 square equal to m2 v2 square minus m2 u2 square. And by taking the common m1, that is u1 square minus u2 square equal to m2 v2 square minus u2 square. And from the formula a square minus b square, that is a minus b into a plus b, from this we can write m1 e1 minus v1 whole into e1 plus v1. Similarly, which is equal to m2 into v2 minus u2 plus v2 plus u2. It is equation number 3. And from the law of conservation, it is the equation number 1. What is our target? To find out the v1 and v2 in terms of m1, m2, u1 and u2. And there are two unknowns, and we already have two equations here. Therefore, we can easily solve. This is the basic rule for the algebra. Number of unknowns and number of equations would be same. Number of equations may be more than the number of unknowns, but when the number of equations less than the number of unknowns or variables, then you cannot solve it. Here there are two unknowns, v1 and v2, and we have two equations. Equation number 1 and 2, both are same equations. And now from the 2 and 3 equations, the equation 3, it is coming from the law of conservation of kinetic energy, and equation 2, that is coming from the law of conservation of linear momentum. Now dividing the equation 3 by the equation 2, that means equation 3, it is the 3 and it is the equation 2. And when we divide the equations, left hand side divided by left hand side and right hand side divided by right hand side. The left hand side of the equation 3, that is the m1 u1 minus v1 whole into u1 plus v1. And left hand side of the equation number 2, that is m1 whole into u1 minus v1, which is equal to m2. Right hand side of the equation number 3, m2 whole into v2 minus u2 whole into v2 plus u2 divided by m2 into v2 minus u2. Now it is clear. Now m1 m1 m2 m2 v1 minus v2 v1 minus v1 u1 minus v1 u1 minus v1. Similarly, this is v2 minus u. They cancel out each other, and ultimately we get a very simple, very fair equations. That is u1 plus v1 is equal to u2 plus v2 plus u2. And from that, again, we can write u1 minus u2, that is the relative velocity of the approach. It is nothing but the relative velocity of approach, which is equal to v2 minus v1. That is relative velocity of separations. And already we have stated that it is the basic criteria for the elastic collision, and it is now proved that the relative velocity of approach, that is before the collision, and relative velocity of separation after the collision, these are the equal. These are now proved. So relative velocity of separation of body A, it is the for body A, 1 is for body A, and 2 is for the body B. Relative velocity of body A with respect to body B. That means here we subtract the u2, that means relative velocity with respect to P, which is equal to relative velocity of B. That means v2 minus v1, relative velocity of B with respect to A. It is relative velocity of A with respect to B. With respect to means this velocity is subtracted, therefore with respect to B, and it is the relative velocity of B with respect to A. These two are equal. Or relative velocity of approach before the collision equal to relative velocity of separation after collision, and that is v2 minus v1 whole divided by u1 minus u2, that is the 1. That means it is nothing but the coefficient of restitution. The value of the coefficient of restitution in this example, one-dimensional elastic collision, that is now proved equal to 1. And if you was to prove that in case of elastic collision, the value of E is the 1, we can easily now prove in this way, that is v2 minus v1 divided by u1 minus u2, that is the E. And in this example, it is 1. Therefore, E is the 1. So it is proved that coefficient of restitution or resilience of perfectly elastic collision in one dimension is unity, and now it is proved is the 1 for the elastic collisions. Now our next target is to find out the v1 and v2, that means velocity of object A after the collision and velocity of object B. First of all, velocity of A from the equation 4, that means we already know this equation 4. From this, if we put the value of v1 in the equation, then we get v2, and if you put the value of v2 in the first equation means equation coming from the law of conservation of linear momentum. If we put the value of the v2 here, then we can find out the v1, and if we put the value of the v1, then we can find out the value of the v2. And first of all, when we want to find out the velocity of A, then we have to put the real velocity of v2 B, that is v2 is from this equation u1 minus u2 plus v1. And by putting this v2 in equation 1 means m1 v1 plus m2 v2 is equal to m1 e1 plus m2 u2. That is from the law of conservation of linear momentum. The v2 is the e1 minus u2 plus v1. Now multiplying this, m1 v1 plus m2 u1 minus m2 u2 plus m2 v1, which is equal to m1 u1 plus m2 u2. Now we have to find out the value of v1. Therefore, we are taking the v1 as a common here, and from these two we get, if we take the v1 common, the m1 plus m2, and these are the in the left hand side. When they move to the right hand side, the plus minus become plus and plus become minus, and from that m2 u1 and m1 u1, and when it moves toward the right hand side the equation, then m1 minus m2 into u1, and it is the m2 u2 minus, and therefore it is a 2m2 u2. And by dividing right hand side and left hand side by m1 plus m2, we get the answer. Therefore v1, that is the m1 minus m2 whole into u1 divided by m1 plus m2 plus 2 into m2 u2 divided by m1 plus m2, and it is a very standard formula for the one-dimensional elastic collisions. Now what will be the velocity of the first object, the A object, after the collision at v1 in terms of m1 m2 u1 u2, that is m1 minus m2 divided by m1 plus m2 into u1. That is first one. We have to find out the first one, velocity of the first one, and plus 2 m2 u2 divided by m plus m2. Now similarly you can find out the velocity of the b, and from the equation 4, if we put the v1 is equal to u2 minus u1 plus v2 in the equation, first equation, that is equation from the law of conservation of linear momentum, and m1 v1 is the u2 minus u1 plus v2 plus m2 v2, that is equal to m1 u1 plus m2 u2, and now multiplying it, m1 u1 u2 minus m1 u1 plus m1 v2 plus m2 v2, which is equal to m1 u1 plus m2 u2. And again, by taking the v2 as a common, m1 plus m2 into v2, that is equal to 2 here, 2 m1 u1 plus m2 minus m1 into u2. That is v2 is that 2 m1 u1 divided by m1 plus m2 plus m2 minus m1 divided by m1 plus m2 whole into u2. That means these equations, it is the equation for the v1 and it is the equation for the v2. Just they interchange the places, similar type of expressions, and these two are the standard formula for the velocity of the collisions in one-dimensional motion. Now some special cases. Let us suppose case 1, when the colliding bodies have equal masses, that is m1 equal to m2 equal to m. Let us suppose m, mass of each object same, and elastic collision taken place. That means what will be the velocity of A after the collisions? That is first object, and that is the v1. We already derived the formula for the v1, general formula, that is m1 minus m2 divided by m1 plus m2 whole into u1 plus 2 m2 u2 divided by m1 plus m2. Now by putting the value of m1 equal to m2 equal to m, the m minus m divided by m plus m is plus into u1 plus 2 into m u2 divided by m plus m, and obviously it is the 0, m minus m is the 0. So 0 into 1, that is the 0, and it is the 2m divided by 2m u2, that is u2. That is v1 is the u2. That is velocity of the body A after collision. That is velocity of the body B before collisions. That means the velocity of the B before collision, it was u2, and after collision this velocity is gained by the first object. Now v2, what will be the v2? The v2, the formula is the 2m 2u, this m plus m, it is m minus m, this one, and it is again 0, and 2m divided by 2m u1, that is the u1. The v2 is the u1. Velocity of the body B after collision equal to velocity of the body A before collisions. These two are equal. Now velocity B collision, that means we can say when two bodies of equal masses suffer one-dimensional elastic collision, then their velocity is interchanged after collisions. If two masses in one-dimensional collision, they collide to each other, and at that time their velocity interchange. That means velocity of A and velocity of B before the collision. After the collision, the velocity of A will be the velocity of B. Velocity of B before collision. After the collision, velocity of B, that will be velocity of A before the collisions. Interchange. Velocity is interchange in this case. When case number 2, when the body B is initially at rest. So here initially rest, that means v2 is 0. And from the above equation, we can find out all the conditions, such type of condition. Now putting this is the 0. Obviously, V1 that will be M1 minus M2 divided by M1 plus M2 into U1. And V2, again V2 that is 0, that is the 2 into M1 U1 divided by M1 plus M2. That means if you know about two equation V1 and V2 general equations, in this case also you can solve by putting the U2 0, U2 0. If the target object, second object is known the target object, initially it was rest. But after the collision, it will gain some velocity, and that velocity will be 2m1 u1 divided by m1 plus m2. Now, when m1 is equal to m2 is equal to m and u2 is a 0, let us suppose second object it was at rest and mass is also the same. Then what will happen? In such a case, the v1 will be 0. And after collision, the first object which was initially, that means before the collision was motion, that will be at rest after the collision. And here also the velocity interchange taken place, and the v2 that will be u1. From when we want to find out v2, that is the 2m divided by 2m into u1, that is the v2 is the u1. Thus, in elastic one dimensional collision, if the body collide with other body of same mass at the rest, then they just interchange their velocities. In the above cases also, it is not so necessary the second object when it was rest, but it is prominently observed. If the one object is striking other object which is at rest and their masses are equal and the collision, elastic collision, then it is interestingly you will observe the moving object that will be at rest at the same position and with the same velocity, the second object which was initially rest, that will move with the velocity of previous one. Now another cases, let us suppose the m1 very greater than m2. So when m1 very greater than in the above cases and the second object is at rest, that means m1 greater than m2 means when we add or subtract m2 with m1, we can neglect easily the m2. Then from this equation, if we neglect the m2 here, m2 here, that is v1 is the u1. That means if the projectile object it is very massive, then there will be no change of the velocity. v1 will be the u1, and that means velocity of that projectile object which is striking the object which is at rest. The mass of that object is very less compared to the projectile object, and such cases there will be no change of the m1 velocity m1, that will move along the same direction with the same velocity. But what will happen for the second object which is very lighter comparable to the uh, projectile object, which is at rest, it is not the target object. In such a case, initially it was rest, but here if we put the value v2, that is 2m divided by 2m1, and m2 is neglected here because m2 is very less. In such a case, the v2 that will be 2u1. Thus, when a heavy body collide with a light body at rest, then heavy body remains moving with same velocity, whereas the stationary light body begins to move with twice the velocity of heavy object or heavy body. That means initially it was rest, but it will move with double of the velocity of the striking object or projectile object. Very interesting. And similarly, we can consider the M2, which is at rest. It is very massive than the striking object, that is M1 less than M2. Then M1 can be neglected. And in this equation, when M1 neglected, therefore we get the V1 is the minus E1. And that means, and V2 obviously, V2, if we neglect it, then V2 will be the 0. That means the which massive object which was initially at rest, it will remain at rest. But the object which is the strike the heavy object, it will collide after the collision. When light body collide with the heavy body at rest, then it rebounds. V1 is the minus E1, rebounds with its original velocity, whereas the heavy body practically remains as rest. Now all the discussion above related to the elastic collision. Now inelastic collision in one dimensions, let us two bodies of mass m1 and m2 moving with velocities e1 and e2 respectively along a single axis, and let us say maybe that is along the x-axis. They collide involving some loss of kinetic energy, and therefore the collision is inelastic, and V1, V2 be the velocities of the two bodies after the collisions. Here we cannot use the law of conservation of kinetic energy. Some amount of kinetic energy is lost in the form of other form of energy like heat energy, light energy, etc. As the two bodies from one system which is closed and isolated, that means there is no other forces acting on the system, we can write the law of conservation of linear momentum for the two body system as, therefore total momentum before collision, that is the P initial before collision with the Pi initial, that is the total momentum after collision. You can always write this. You can always write this. Law of conservation of linear momentum always valid for all types of collisions. That is m1 e1 plus m2 u2 is equal to m1 v1 plus m2 v2. If we know masses of m1 m2, initial velocities u1 u2 are and one of the final velocities, we can calculate other final velocity. That means here there is limitations. There are two unknowns here, but we have only one equations, and that is coming from the law of conservation of linear momentum. V1, V2, there are two unknowns. Here we cannot write the equation for the law of conservation of kinetic energy. So we cannot find out the values. We can get only one equations here, but there are two unknowns. And if we can find out V1 either or V2 in other method, then we can solve, we can find out the other values. So it is the limitations of this process in case of inelastic collision. Therefore, we have to calculate the V1, V2 with the help of other fact also, experimental or other fact. But for the perfectly inelastic collision, we can find out the velocity after the collisions. Let us suppose perfectly inelastic collision in one dimensions, and let us consider two bodies A and B having masses m1 and m2 respectively. Let us the body B is initially at rest. A body of mass m1 moving with velocity u1 collide head-on with another body of mass m2 at rest. After the collision, the two bodies stick together and they move together with a common velocity v. That means before the collision, let us suppose mass m1 of object A, it has initial velocity 1, and another object B, mass m2, initial velocity 0, that is initially it is rest, and after the collision they stick together and they are moving with a common velocity v. So we can find out here the velocity v. Even if u2 not equal to 0, then we can also find out, because there is only one unknown, only common one velocity v, and obviously we can get the one equation from the law of conservation of linear momentum. So linear momentum before initial, that is before collision, equal to linear momentum after collision, that is m1 e1 plus m2 u2, which is equal to, we can write m1 plus m2 into v, because they stick together and they are moving with a common velocity v. So m1 e1 plus 0, because we are considering the second object B, initially it was at rest, there is no initial velocity before the collision, it was at rest, therefore m1 e1 plus 0, which is equal to m1 plus m2 into v. Even if it is it has velocity, there is a u2, then m2 u2. At that time also we can find out the velocity v. The v is the m1 e1 divided by m1 plus m2. That means single unknown and single equation, these are known to us, m1 e1 m2 u2, all these are known to us, therefore we can find out the final velocity. Knowing m1 m2 and u1, we can calculate the final velocity v as the mass ratio, that is m1 by m2, m1 by m1 plus m2 obviously less than 1, because it is the numerator, denominator is m1 plus m2, it is more than m1, therefore it is less than 1, that is a fraction. Therefore u1, that will be less than the v. That means sorry, u1 is greater than the v, that is final velocity will be less than the u1, initial velocity before the collisions. We can calculate loss of kinetic energy in these collisions. Here we can calculate loss of kinetic energy before the collision. The kinetic energy E1, that is the half m1 E1 square, and total kinetic energy after the collision in this example, that is the E2 half into m1 plus m2. Now the mass all together, that is m1 plus m2 into v square, v the common velocity. Now from the above equation, if we put the value of the v, and therefore final kinetic energy, kinetic energy after collision E2, that is half into m1 plus m2 whole into m1 e1 divided by m1 plus m2 whole square, and that is the half and m1 and plus m2, and below this line m1 plus m2 whole square. Therefore, after the calculation, we get m1 square e1 square whole divided by 2 into m1 plus m2. Now, when we want to find out the loss of kinetic energy, obviously that is the kinetic energy before collision and minus kinetic energy after collision. And if it is a positive number, then we can definitely say there must be a loss of energy. That means if it is positive one, then obviously the kinetic energy before collision was more than the kinetic energy after collisions. Let us find out what will be happen. Loss of kinetic energy, that is the kinetic initial kinetic energy half into m1 e1 square minus m1 e1 m1 square e1 square divided by 2 into m1 plus m2. Therefore, m1 e1 square, just cross multiplication, 2 LCM is that 2 m1 plus m2, the m1 plus m2, that is m1 e1 square whole into m1 plus m2 minus m1 square e1 square. And now there is m1 square e1 square plus m1 m2 e1 square minus m1 square e1 square, and these two are cancelled out, and finally we get that is the m1 m2 e1 square divided by 2 into m plus m2. Here we are definitely saying the kind loss of kinetic energy, because this difference, it is the initial kinetic energy minus kinetic energy, and it is a positive number. How it is positive number? Now m1 m2 m1 plus m2, all these masses, and there is a plus sign, therefore these are not any negative quantity. And maybe u positive or negative, but e1 square always positive one, because any square term never be negative. Therefore m1 m2 e1 square whole divided by 2 into m1 plus m2, which is positive. Therefore some kinetic energy is always lost in an elastic collision, practically in a perfectly elastic collision. In a perfectly elastic collision, we can say it is a proof that in a perfectly elastic collision there must be loss of kinetic energy, and this kinetic energy obviously transform into other form of energy. Now all these are elastic collision, inelastic collision, perfectly elastic collision, all the above discussion taken place when before the collision and after the collision, all the colliding objects are moving along the same straight line. That means one-dimensional collisions. But in our daily life and real life, always the collisions, generally oblique collision or two-dimensional collision, even if three-dimensional collision also. Here we will consider the elastic collision in 2 dimensions, or oblique collision, elastic collisions, or 2-dimensional oblique collisions. Here we will learn how we frame the equations, because when we find out any unknown quantity, we have to frame some equations, and we have to take some relations, and number of equations will be more than the number of variables, then we can solve them. Now here we will learn how can we frame the equations for oblique collision or 2-dimensional elastic collisions. Here let us consider two bodies A and B having masses m1 and m2. Let us the body of mass m1 moves with velocity e1 and collides with the body of mass m2 at rest. After collision, let us the two bodies move with velocities v1 and v2 at angles theta and phi with x-axis. That means here the figure diagram, schematic diagram, let us suppose the m2 object, B object, which mass is the m2, it was initially at rest, u2 0. Here also we are considering, it is not so necessary, it is the simplest case one, it is not so necessary always the u2 will be 0. It may be another velocity, but here in this example it is the simplest one. We are considering that object B, whose mass is m2, it was at rest, and it is known as the target object, and it is known as the projectile object of object A, mass m1, and e1 is the velocity, and it is moving towards the target object B, and the collision taken place. And after the collision, the object A that is moving along these directions, and initial direction of the A, we are considering that initial direction of the A, that is along the x-axis, or we are taking the x-axis along the initial direction of the object A. And after the collision, here collision taken place. After the collision, the A, it is moving, let us suppose with some angle theta with the x-axis, and this theta is used to give the directions of the movement of the object A after the collisions. And at the same time, we are considering B is moving along this by making an angle phi with the x-axis. And phi and theta, these are also now unknown. Now one number of unknowns is increasing here. And V1, the velocity of A after the collision, that is the V1, and velocity of B after the collision, the numerical value is the V2. And now there are four unknowns: V1, V2, theta, and phi. And knowns are U1, U2, M1, M2. These are known to us, but there are four unknowns. Now, how can we solve? How can we find out the four unknowns with the help of the different equations? Let us construct equations. It is a fact, and that is this move axis, and it is taken place after the collisions. And in such a cases, generally we are taking the origin where the collision taken place. That point is taken at the origin of this system before the collisions. Now, x component of momentum, that is the px m1 e1, that is the m1 e1, and y component of the, that is the py, no particle components. Here, after there are two components of the momentums. Here always we can use the law of conservation of linear momentum, but in two-dimensional motion, when we apply law of conservation of linear momentum, we have to apply it separately along the x-axis and separately along the y-axis. Along the y-axis, that means because momentum, it is a vector quantity, we can consider the components of the momentum before the collision along the x-axis, and after the collision, x-axis separately conserved, and momentum before the collision along the y-axis, and after the collision along the y-axis separately conserved. That means from the law of conservation of linear momentum, we will have two equations along the x-axis, along the y-axis. In case of three-dimensional collision, we will get three equations along the x-axis, along the y-axis, and along the z-axis. Here we considering two-dimensional collision. That means we have to consider the along the x-axis total component before and after, and along the y-axis total component before the after. Since there is no velocity component along the y-axis, therefore before the collision there was no linear momentum along the y-axis. Therefore, x component of the momentum px, that is m1 e1 plus 0, that is m1 e1, and y component of the momentum, that is the py 0, no vertical motion, no vertical component. These are the px and py. These are the initial linear momentum along the x-axis, and initial momentum before collisions, and py is the 0. There is the y component of the moment, all momentums before the collisions. After the collision, the component of the momentum of mass m1 and m1. Now let us figure diagram. v1 cos theta is the x component of the velocity, and v1 sin theta y component velocity. Similarly, v1 m1 cos of theta, that is the x component of momentum, and v1 m1 v1 sin theta, that is the y component of the momentum after the collision. And here also the v2, that is m2 v2 cos of phi, this is the phi, m2 v2 cos of phi, it is the x component of the momentum of the second object, and m1 m2 v2 sin of phi, that is the y component of the momentum, but it is along the negative y-axis. It is along the negative y-axis, but this y component of the momentum of object A, that is along the positive y-axis. It is along the, but along the x-axis, both are along the same direction, m1 v1 cos of theta and m2 v2 cos of phi. So after the collision, the component of the momentum of mass m1, that is the m1 v1 cos of theta along x-axis, and number 2, m1 v1 sin theta along the y-axis. Similarly, the component of the momentum of mass m2 are m2 v2 cos of phi along the positive x-axis, and m2 v2 sin of phi along the negative y-axis. Therefore, x component of the momentum after collisions, that is px dashed, that is m1 v1 cos of theta plus m2 v2 cos of phi, and y component of momentum after collision, that is py dashed, m1 v1 sin theta minus m2 v2 sin of phi. As the collision is elastic, so both momentum and kinetic energy conserved. Let us suppose initially we are taking the consideration of law of conservation of linear momentum, and according to law of conservation of linear momentum, px dash equal to px. That means all the x component of the linear momentum after the collision must be equal to the all the linear component of the x component of the momentum before the collision, and now it is m1 v1 cos of theta plus m2 v2 cos of phi is equal to m1 e1, and in along the y-axis it is m1 v1 sin theta minus m2 v2 sin of phi equal to 0, because there was no linear momentum along the y-axis before the collisions. Now there are now two equations. Also we get another equation from the kinetic energy. Here we are considering the collision, it is a elastic collision, therefore the total kinetic energy before the collision equal to total kinetic energy after the collision. Since kinetic energy it is a scalar quantity, it has no components. We cannot take the x component of kinetic energy and y component of kinetic energy. And if you take, you will get the single equations again. But we are not taking that. We are taking the kinetic energy conservations. Only one single equation you can get. That is the total kinetic energy half m1 e1 square, because second object initially it was rest. That is half m1 v1 square plus half m2 v2 square is equal to half m1 e1 square. Now there are four unknowns. Be careful: theta, phi, v1 and v2. But we have only three equations. We have to calculate the values of four variables: v1, v2, theta and phi. But there are three equations, 1, 2, 3, which is not possible. By measuring one of the four unknowns, say theta, experimentally the value of other unknown can be solved. That means here we are learning how we get different equations. But there is another limitations here. There are four unknowns, but we can only get three equations. Therefore, we cannot solve. It is the basic rule of the algebra: number of unknowns and number of equations should be same or more than the number of unknowns. Here there are four unknowns, but we get only three equations: two equations from the law of conservation of linear momentum, and one equation from the law of conservation of kinetic energy. Therefore, we cannot solve it, and we only can solve it if we know any one among the four quantities by other method, by experimental method. Now one special case: elastic collision in two identical particles. Let us two identical masses m1 and m2 and m, and elastic collision, two-dimensional collision, and from the equation, this law of conservation of kinetic energy, since it is elastic one, we can write half m v1 square plus half m v2 square equal to half m into u1 square. Half m, half m, half m, all these are common, therefore we can write u1 square is equal to v1 square plus v2 square. Let us suppose it is one equations, and we get v1 square, u1 square is equal to v1 square plus v2 square from the law of conservation of kinetic energy. By conservation of linear momentum, we can write here m1 u1 vector plus m1 v1 vector plus m2 v2 vectors. Here when we write in the vector form, we can write only one equations. But when we take the components, we can write along the x-axis, along the y-axis, along the z-axis, if it is in three-dimensional case. But when we write the vector form, the both components are including within the u1 vector, m1 vector, and v1 vector, v2 vectors. Therefore, in the vector form, we can write only this one. That from that we get u1 vector equal to v1 vector plus v2 vectors. That is u1 vectors. From this, if we vectorically add them, then we get this u1 vectors here. Vectorically, if we add vectorically, again we get v1 vector plus v2 vector, and that is the u vector. In case of when masses are equal, here obviously here we get when we are considering when masses are equal. So we get now this one, and from the dot product we can write here left hand side dot left hand side equal to right hand side dot right hand side. That means u1 vector dot e1 vector equal to v1 vector plus v2 vector dot v1 vector plus v2 vectors. That means dot with left with the dot with the right, this one. And we know the u1 vector dot u1 vector, that is u1 square. A vector dot a vector, we know that is a square. B vector dot b vector, that is b square. Similarly, u1 dot vector u1 dot vector is equal to u1 square, and that is now distributing this dot product v1 vector dot v1 plus v1 vector dot v2 plus v2 dot v1 plus v2 dot v2. Now v1 dot v1 vector, that is the v1 square, v2 dot v2 vector is the v2 square, and it is the 2 into v1 dot v2. Now we know this v1 vector plus v2 vector, that is u1 vector. and from this it is the u1 v2 sorry v2 v1 square plus v2 square is the u1 square. Therefore from we can write it is equal to u1 square equal to u1 square plus 2 into v1 dot v2. That means this cancel out. We get 2 into v1 dot v2 is the 0. It is the 0, and that means v1 dot v2 is the 0. That means v1 v2 cos of alpha 0, where alpha is the angle between the v1 and v2. Therefore cos of alpha 0, that is the alpha is the 90 degree. And already we know if the dot product of the two vector is 0, then these two vectors will be perpendicular to each other. So when the two masses are equal, it is now proved that after the collisions, they will move with the right angle to each other. Angle between v1 and v2 will be 90 degree. Hence, two identical particles move at right angles to each other after suffering elastic collision in two dimensions. And the collision is the, let us know, collision is the elastic one, number one, and the masses of the two colliding objects are same. Then after the collision, they will move right angle to each other. That means angle between the two will be 90 degree, and you can easily prove with the help of this dot product method. You can find out this. Now one term is sometimes used, that is the glancing collision. It is nothing but when one object is projectile object just touch and passes away. Then this type of collision, when the collision is glancing collision, that is when theta is the 0 degree and phi is the 90 degree. From equation 1 and 2, theta 0 degree and phi is 90 degree. From this one equation, when theta 0 degree and phi is the 90 degree, the cos of phi is the 0, cos of 90, that is cos of phi is the 0. Therefore m1 v1 cos of 0 means 1, m1 v1 is the m1 u1. That means v1 is the u1. Therefore there would be in this type of collision when theta is the 0 degree, phi is the 90 degree. In such a case, m1 v1 equal to m1 u1, that is v1 is the u1. And in the from the second equations, m1 v1 sine of 0 degree minus m2 v2 sine of 90 degree is the 0. And from that we get the v2 is the 0. That means kinetic energy of the target object that's 0. Hence, when collision is the glancing, then the incident particle does not lose any kinetic energy and scattered almost undeflected. That means it just touch and pass the object. Therefore, there will be no loss of kinetic energy. In glancing collision, there is no loss of kinetic energy. Also, that there is no change in the velocity. Now it is the end of these lessons, and we will meet with our next lessons. Bye.